All right, so the unit that we are covering is called thermal energy and heat transfer. So we're looking at how heat is transferred and thermal energy versus temperature, what the difference is between those two. So thermal energy is the total of all kinetic and potential energy of all the particles in a substance. Now, we have talked about the sum of kinetic and potential energy before. What were we talking about then? What was the sum of potential and kinetic energy? That was mechanical energy. Good. Okay, so with the mechanical energy, we were looking at something that's macroscopic. So you're looking at an object as a whole. You're looking at something like a ball, or when your example that you were working with was, we're looking at the car as it's rolling down the hill. All right, so you're looking at things on a macroscopic level. With the thermal energy, we're looking at a microscopic level. So what's happening with the particles themselves? So thermal energy, it says the total of all the kinetic and potential energy of all the particles in a substance. Okay? So what would happen all right, so if I have something like, let's say we have a beaker of water. And I know that in a beaker of water, we're going to have millions of particles. We're not going to be doing that. We're going to be simplifying it. All right. So this is just an example, but again, it's a very simplified example. All right. So thermal energy says, and I'm just going to put 10 particles here. Okay. And they are 1 joule apiece. And we're looking at just kinetic energy. Okay. Thermal energy says you are summing up all the potential and all the kinetic energy for a system, in this case, this beaker of water. All right. On your PowerPoint that you're looking at, we know that kinetic energy is energy based on what? What do you have to be doing in order to have kinetic energy? It has to be moving. Okay, what's the equation for kinetic energy? Hasn't changed. Kinetic energy equals, good, 1/2 mv squared, 1/2 mass times the velocity squared. So if your velocity is increasing, your kinetic energy is increasing, right? When we're talking about the mechanical energy and potential energy, gravitational potential energy, what was that based on? Gravitational potential energy. So mass times gravity times, which is your gravity. So mass mg times what? Times height. And the higher up you were, right, from the surface, the more potential energy that you have. With the thermal energy, since we're talking about particles, what is important is the distance or the separation between the particles. So the greater the separation, the greater the potential energy. All right? And then what you do, so when I'm looking at this system, what I'm going to do is I'm going to add up the energy, that's kinetic energy, having to do with the motion of each of the particles, plus looking at the potential energy that's based on the separation between the particles. All right? But just to simplify this, we're not going to worry about the potential energy part of thermal energy. So let's just look at the thermal energy. If I have 10 particles up here, and each of them has 1 joule of energy, then what would be my thermal energy? Again, really simplified example. So it says that thermal energy is the sum, the total of all the energy. So what would this be? If I have 10 particles in a system, and each of them has an energy of 1 joule, it would be 10 joules. Okay? All right. So just remember that your thermal energy is going to be the total. Now let's look at something else. We're going to compare this. Your temperature. All right, so temperature is related to the average kinetic energy of the particles in a substance. The average kinetic energy. Kinetic energy, again, is based on your speed. So it says atoms in an object are in constant motion. That means even if I have like a solid, this container is solid, all right? Even though the particles are fixed in position, they can't move around, they still vibrate in whatever position they're in. So they are in motion. What happens is when they move faster, your average kinetic energy is going to increase, and that means your temperature is going to increase, okay? If they slow down, since kinetic energy is based on speed, then kinetic energy will be lower, and that means your temperature is going to be lower because your temperature is a measure of your average kinetic energy. Okay, now, if I was looking at the average grade for everyone in this class, okay, if I calculated the average for this class, does that mean that everybody in this class has the same grade? No. Okay, so average would mean that in a system, how do I get the average? How do I get the average? You do what? Good. Okay, so you add up all the numbers. If I was looking at the average grade in here, I add up everybody's grade, and then I divide by the number of students that I have to get the average for the class. For the temperature, it says temperature is a measure of the average kinetic energy. So what happens is I need to add up the kinetic energies for all the particles that are in the system and divide by how many particles that I have, okay? So again, to simplify this, we said that, so I'm not going to give them all different values, it's just going to be 1 joule, all right? So each one of these has a kinetic energy of 1 joule, and I have 10 particles. So average kinetic energy, your temperature is a measure of your average kinetic energy. Okay, so 10 particles, 1 joule apiece. What would be the average energy here? It would be 1, because what do I have? If I add them all up, how many joules do I have? 10, and then I would divide by what? By 10, because I have 10 particles. So my average is 1 joule. Okay, so here you can see that your thermal energy and your average kinetic energy are going to be different, all right? As far as when you are measuring temperature, it has to do with what your average is. Okay, so let me make up another example. Let's say what happens is I have another beaker of water, but it only has 5 particles in there, and they are still 1 joule apiece. Now what will be the thermal energy? 5, because you're adding them all up, right? 1, 2, 3, 4, 5, so that's a total of 5 joules. What would be the average kinetic energy? Okay, which is related to your temperature. It's going to be 1 joule. Okay, so look at this. What happens is I have 1 joule here, but there's more volume, right? Here I have 1 joule with less volume. Your temperature is based on the average kinetic energy. So as long as the average kinetic energies are the same, that means these have the same temperatures. It has nothing to do with volume. Okay? All right, so has nothing to do with volume. On the other hand, your thermal energy is going to be based not only on the kinetic and potential energy, right, but also the number of particles. So even though these particles all have the same, because I made them 1 joule, all have the same amount of energy, thermal energy, you're adding them up, and since this has more volume to it, there are more particles in this, it's going to have more thermal energy, okay? So you can have the same temperature, but have different thermal energies. Are there any questions on that part? All right, let's go on with the notes. Okay, on the next section of your notes, okay, you have an area where you're going to be drawing your thermometers. You don't have to make it as fancy as this. You can just draw a line, and you're only focusing on the Celsius and Kelvin scale. So go ahead and take a moment to draw these. You draw a vertical line, and then you need to write down here temperatures at which water boils, water freezes, and absolute zero, and then make sure that you actually label those. Okay, so go ahead and take a moment to do those. Okay, so looking at your temperatures, you have for the temperature at which water boils, you have on a Celsius scale, it's 100 degrees, and a 373 on the Kelvin scale. Okay, on the water freezes at 0 degrees Celsius, 273 on the Kelvin scale. For absolute zero, it's negative 73 degrees Celsius, and then it's 0 on the Kelvin scale. So, looking at this, if I was moving from, let's say I had a Celsius temperature and I was trying to change it to Kelvin, what would you need to do? So looking at water boils, it's 100, and I need to go to 373. 0, you go to 273. Negative 273, you go to 0. All right, what would I need to do in order to change a Celsius temperature to Kelvin? You're going to add 273. Good. All right, so vice versa, if I had Kelvin temperature and I wanted to change it to Celsius, what would I need to do? Good, subtract 273. All right, so down below that you have an area for you to write the temperature as far as the equation. So if you have a Celsius temperature, Celsius plus 273 is going to be your Kelvin temperature. So if I have a temperature of 10 degrees Celsius, what would be my Kelvin temperature? If I had a temperature of 10 degrees Celsius, what would it be in Kelvin? Anybody? It would be 283, because it's going to be 10 plus 273. And then if you're given a Kelvin temperature, let's say that our Kelvin temperature is 293, right here. Kelvin temperature is 293. Then what would the temperature be in Celsius? 293 minus 273? It would be 20. Good, it would be 20 degrees Celsius. All right. One last thing that I want to talk about, what's on this scale, it says absolute zero. Okay, so absolute zero is right here, and it's 0 Kelvin, or if you're looking at the Celsius scale, it's a negative 273 degrees Celsius. So we know that temperature is a measure of the average kinetic energy. As your average kinetic energy drops, because particles are slowing down, what happens to temperature? As your average kinetic energy goes down, what happens to temperature? It's going to decrease. Okay, so what happens is particles are getting slower, your temperature is going to be dropping. So that means even if you're looking at something like a solid where the particles are just vibrating in place, vibrations are slowing down. As the vibrations slow down, temperature is going to be dropping. Okay, vibrations slow down, slower speed means lower kinetic energy. Lower kinetic energy, lower average kinetic energy means lower temperature. So when we get down to 0 Kelvin, right here, 0 Kelvin is the point where there is absolutely no motion. So your particles have slowed down to the point where they are not even vibrating. No vibrations, no movement whatsoever. Can you get any slower than that? No. All right, that is as slow as you can get. So at that point, what we have is 0 Kelvin. 0 Kelvin means 0 movement. There's no kinetic energy, nothing going on right now. All right, so theoretically, this is the lowest temperature you can get because this is where particles stop moving completely and there's no vibration, and that is called absolute zero. All right, thermal energy relationships. So looking at what we have here, first point says, as temperature increases, so does thermal energy. As temperature increases, what's happening to your kinetic energy? Your average kinetic energy is increasing. So remember with your thermal energy is, when you're looking at thermal energy, it is a total of kinetic and potential energy. So as your temperature is increasing, if you're increasing your kinetic energy, then your thermal energy will also increase. So not only does your average kinetic energy increase, but the thermal energy is going to increase also. second point here says, even if the temperature doesn't change, the thermal energy in a more massive substance is higher because it is a total measure of energy. So that is actually what happens here, the example that I gave you here on the board. All right, the example that I gave you here on the board. What happens is we kept the average kinetic energy the same, which means the temperature is going to be the same here. But because there are more particles in here and we're adding up the energy for all the particles, because there is more here, so a bigger volume here, the thermal energy is going to be more. Okay? Now, I'm going to change this. All right, so let's take a look at this question that I'm putting up on the board. My question is, so what we just talked about says that you can have the same average kinetic energy, so that the same temperature in 2 beakers of water. The one with more water, bigger volume, is going to have a greater thermal energy just because there are more particles, right? Because we're just summing it. So here's my question. If I have 2 beakers of water and their average kinetic energies are different, so let's say what happens is this one has an average kinetic energy of 1 joule, but as far as what's going on in here, we have an average kinetic energy of 2 joules. Number one, which one is going, this is A, this is B, which one is going to have a higher temperature? The second one, why? Because it has more joules as far as your average kinetic energy, and temperature is a measure of the average kinetic energy. So since the average kinetic energy here is higher, this is going to have a higher temperature. So here's my question. If we have 2 beakers of water that are at different temperatures, is there a way to make their thermal energies the same without changing their temperatures? So their temperatures are going to still remain different. Their average kinetic energies are still different. What can I do to make the thermal energies, these values, the same? So take a moment and talk to the people that you were talking to earlier. All right, what do we come up with? Volunteer, what do we come up with? How can you make these thermal energies the same? I heard discussion going on. Come on, share. What'd y'all come up with?
You could try decreasing the volume.
Of which one?
The second one.
This one? So you're saying have a smaller volume here? Okay, so let's say, for example, let's say that I have a total of, I'm going to make 5 particles here. Each are 2 joules apiece. So what's my thermal energy here? 10 joules. 2 joules times 5 particles is 10 joules. All right, so I want to make this thermal energy 10 joules. I want that to be 10 joules also. So how many particles would I need? 10, because these are 1 joule apiece. So if I have 10 particles times 1 joule, then this is going to be 10 joules each. So yes, that is correct. If you have something that there are different temperatures, if you make the volume of your, the one with the higher temperature, you have a smaller volume. Increase the volume of the other one. Because remember, it's just a total. Thermal energy is just a total. You just need to add them up. So the more particles you have, the more thermal energy you're going to have. All right, so to make these the same, if they're at different temperatures, the one with the higher temperature, you're going to have a smaller volume than the one with the lower temperature. Okay, any questions on that? All right, so the next thing that we're going to go over are the different methods of heat transfer. So first off, it says heat always moves from an area of, so these are 3 things you need to put down for heat transfer. Heat always moves from a warmer place to a cooler place. So heat always goes from hot to cold. Hot objects in a cooler room will cool to room temperature, and cold objects in a warmer room will heat up to room temperature. Sorry, okay, heat always is transferred from hot to cold. Okay. So this has to do with your kinetic energy. When we had talked about the cue ball hitting the balls that are not moving when you're playing pool, the cue ball initially has velocity to it, right? So it has kinetic energy, whereas the other ones are at rest. They have no kinetic energy. When the cue ball hits the ones that are at rest, what happens to the ones that are at rest? What do they do? Do they continue to stay still? No. So when the cue ball, which is moving, hits the ones that are at rest, what do those balls do? They start moving, which means they now have what? What type of energy? Okay, kinetic energy. Where did they get that kinetic energy? From the cue ball. The cue ball, on the other hand, when it hits those balls that were at rest, what happens to the cue ball's speed? It's going to slow down, which means what happened to its kinetic energy? It decreases. Okay, so as far as it losing that kinetic energy, where did that kinetic energy go? Into the other balls, right? So we're looking at a transferred energy. And this is what's happening with your heat. Okay, so as I said, heat moves from hot to cold. If you have something at a higher temperature and something at a lower temperature, which one has more kinetic energy? Has a higher average kinetic energy? The higher temperature. That means those particles are moving faster, right? So think of it in terms of collisions. Those particles that are moving faster are going to collide with something that is moving slower. Particles that are moving slower, they're at a lower temperature. So when it collides, it's going to transfer some of its kinetic energy to the ones that are moving slower. Those particles are going to move that were moving slower are now going to move faster. But the ones that were moving faster to begin with are going to start to slow down. Okay? So your hot material is transferring its kinetic energy to particles that are moving slower or cooler. Okay? Or you understand that? All right. So that's why heat transfers from hot to cold. It goes from a warmer place, a place with more kinetic energy. That kinetic energy is being transferred to something that is moving slower, all right, or that's cooler. So heat is not transferred. You don't have anything transferred from cold to hot, okay? It's always going from hot to cold, warmer to cooler. So it says hot objects in a cooler room will cool to room temperature. So this bottle of water, this was cold earlier, all right? Let it sit here all day. What happens to the temperature? It went up. Because what happens is these were colder, particles were cold. At a lower temperature, particles are moving slower. It's warmed up because what happened to its kinetic energy, the average kinetic energy? In order for it to warm up, what had to happen to the average kinetic energy in this bottle? It increased. Well, where did it get that energy? From the room temperature. So you have particles that are moving out here, right, and colliding with this bottle. They have more kinetic energy, but when they collide with this bottle, that kinetic energy is transferred here. Slows down the stuff on the outside, so it cools down the particles that comes in contact with this. All right. We don't feel it in terms of the room because there's a lot more air in here than there's water in this bottle. Okay, so you're not going to feel the difference. But you can have something like condensation. You sometimes see water forming on the outside of the bottle. That's because those particles that are those water vapor that's coming in contact, when it loses kinetic energy, those particles slow down and change from a gas back into liquid. All right, so that's what's going on. So hot objects in a cooler room will cool to room temperature, such as with this. If you're holding a hot cup, the cup is going to get cooler while your hand gets warmer. Because which way is the heat being transferred? Is it being transferred from the cup to your hand? Which way is heat being transferred, or from your hand to the cup? Which one is hotter? Your hand is hotter than the hot coffee. No, okay, so that is, the coffee is hotter, so you are actually, heat is being transferred from the cup to your hand. That's why it feels hot, because you're actually absorbing heat, okay? When you feel hot, it's because you are absorbing heat from your environment. When you feel cold, on the other hand, that means your environment, whatever you're in contact with, is cooler, and it is absorbing heat from you. Heat always goes from warm to cold. Okay, so it says cold objects in a warmer room will heat up to room temperature. So look at that ice. There's ice in the hand. You can't see the picture that I'm looking at. All right, so ice in the hand. So this is what we're just talking about as far as holding a cup of coffee. All right, heat is going to be transferred. Now, on the other hand, if you're holding a piece of ice, what happens to that ice eventually? It's going to melt, which means it has to be picking up heat. Its kinetic energy has to be increasing. Well, where is it getting the heat? From your hand. It's absorbing the heat from your hand. Your hand feels cold because you are losing heat. When you lose heat, you feel cooler. Okay? So another example is child comes up to their mother, "Mommy, I don't feel good." Mom do the forehead touch, right? "Oh my goodness, you have a fever." Because what does it feel like to mom? On mom's hand, what does it feel like? Feels warm. Feels like child is warm. So who is at a higher temperature right now? Is it mom or the child? The child. So what happens is heat is being transferred from the child to the mother's hand. She is absorbing the heat. That's why it feels warm. Okay? So heat always goes from warmer to cooler. So ice gets warmer while hand gets cooler. Okay. So here's a question to consider. Okay, if a cup of coffee and a red popsicle, doesn't have to be red, purple, whatever color you want, green popsicle, were left on the table in this room, what would happen to them and why? So I'd have a cup of coffee and I just leave it out here. It's hot to begin with. What is going to happen? It's going to be cool down. Why? So think in terms of heat transfer, what's happening? It's hotter than the room, so heat is transferring which way? Good, from the cup to the room. Okay, always goes from the warmer to the cooler, warmer area to the cooler area. So if the coffee is hotter, that heat is going to transfer to the room. Okay, that kinetic energy is going to transfer to the room, to the particles in the room. All right, so what about the popsicle stick? What is it going to do? It's going to melt. I heard it's going to get hotter, so it's going to warm up. Okay, where is it getting the energy? The room. So the heat's being transferred from the room or from the air to the popsicle. Okay, I don't think you had that question. All right, cup of coffee will cool until it reaches room temperature. The popsicle will melt and then the liquid will warm to room temperature. Okay. Next. Heat transfers in 3 ways: conduction, convection, and radiation. All right, so we are going to spend just a few minutes talking about those 3 ways that heat transfers. First one that we are going to start with is your conduction. So you don't have to write all of this down. Just for conduction, where it says the next block over where it says definition, all you need to do is write the first line. Conduction is transfer through direct contact. Direct contact. So here we're talking more like solids, transfer of heat in solids. It says on a molecular level, hotter molecules are vibrating faster than cooler ones. Because they have more kinetic energy. When they come in contact, the faster moving molecules bump into the slower moving molecules and heat is transferred. So that's the same thing as what we're talking about with the pool. Cue ball is moving faster, hits the ones that are moving slower. The slower balls speed up, the cue ball slows down, right? Because we have that bumping happening and then their energy, the kinetic energy is being transferred. So this is how heat is transferred to your finger if you touch a hot stove. Okay, also, has anyone ever cooked on a stovetop and used like a metal spoon or something or to stir stuff around? Would you leave that spoon there, walk away to go do something else and come back and pick up that spoon with your bare hand? I wouldn't do it, okay? So why not? Why wouldn't you do that? This heat from the stove is going to go into the spoon. So the way this happens, let's say that this is a spoon, okay? This part down here, I'm holding it up here. It's not in contact, it's not touching, but down here at the base, this is the part that's in the pan, right? So the heat is being transferred to this because this is currently cooler down here. Speeds up the particles because this is increasing kinetic energy. Particles are going to speed up, temperature is going to increase, right? Particles are speeding up, and then what happens is they bump into the particles that are up here, speeds them up. So they may be moving slow initially, but as this particles start to move faster here, they're going to be bumping into particles that are here, speeds them up. When they speed up, they're going to bump into these more, speeds them up. And remember that when we talk about speeding up the particles, that means your temperature is increasing. So eventually what happens is that heat is going to get to the top here. All right? So that is convection. You have your particles are bumping into each other. All right? So on your paper, you need to have an example. Write down an example or two. So what can you put down for conduction? What's an example of conduction? What I just said. Yes, we could use that one. Anything else? That's actually going to come a little bit later, where the sun that's the third type of transfer that we're going to talk about, the radiation. So conduction, think more of solids that are in contact. Okay, so it could be something like you touch the hot stove by accident, okay, or like the mug itself, that hot coffee, the mug, I can feel the heat on the outside is transferring to my hand, so that's going to be conduction. Okay, so you just need one or two examples. All right, your next one. Next method of heat transfer is convection. Again, you only need to write the first line. So with convection, we're talking about heat transferred in fluids. So whereas conduction was more dealing with solid, this is with fluids. Okay, so fluid is anything that is able to flow. So it doesn't have to be like really liquidy, but water. You can have convection currents in water, something that's thicker, anything that is able to flow. So like magma, do you all know what magma is? So in the earth, as far as layers of the earth, you have the core, you have the mantle, and then you have the crust, right? And the mantle is where you have that magma, that molten material, and it's able to move, flows. All right, so convection, what happens is, think density. So if heat was, and air is another one, talking about convection, so anything that's able to flow. All right, so gases and liquids. Let's say what happens is air. When air heats up, what happens to the spacing between the particles? When air heats up, They separate, they move out. So if you're looking at as far as your density is your mass per unit volume. So if I have like a little space that I'm looking at, a specific amount of space. When air is cold, the particles are closer together, so there's going to be more, it's going to be denser because you have more particles within that space. As you said, when air heats up, the particles spread out. So within that unit space that you're looking at, you're going to have fewer particles, which means your air is going to be less dense, all right? Less dense material always floats on top. It rises. So that is why, as far as oil, it sits on top of water. Okay, a log can sit on top of water. It floats because it is less dense than water. Okay, so less dense material floats. This is why heat rises. Okay, so if you've ever been in a two-story house, this has probably been fixed, I'm hoping, as far as the way that houses are designed. I remember once being in a house, and what happened was it was the, let me see, I think it was during the summer. Air conditioning is running, two-story house, right? What happens is downstairs, it is freezing. But if you go upstairs, it's hot. Because what happens? The air conditioning is running to cool off the air, right? Cooler air is less dense, so guess where it goes? It's all down. Heat rises, so when you go up to the top, it's just like, it's ridiculously hot up there. So here with the convection, you can think the same thing. Let's say that I have water that's sitting on a stovetop and I'm about to boil it. I'm heating it up. It is close to the heating source. The water on the bottom is close to the heating source, right? As it heats up, it's going to spread out and it's going to become less dense. And where's that less dense water going to move? It's going to start to move up, and the colder water is going to sink. But as that water moves up, it's getting away from the heating source, and what's going to happen? It's going to cool down. Plus, here's another thing. It is less dense, but those particles are moving, right? They have kinetic energy, so they have a higher temperature. They collide with other particles on the way up, and they're going to be transferring some of their energy to those other particles, okay? So as they move up, they're losing more and more kinetic energy. They cool down, come back closer together, and then they're going to sink. And it's like a constant cycle. So you end up with what's called a convection current, so, like this. It happens in the mantle. That's where plate tectonics, theory of plate tectonics come in, right? Continental drift. That magma moving is breaking up the continents, the land masses. And then you also see it, videos where you can see like rice boiling in a beaker of water. You can see the rice kind of doing that pattern. So that's convection current. So it's fluid, heated fluid that's heating other fluid, all right, is what convection currents are. All right, so do you have examples? Did you write down examples for your convection current? What are some that we just talked about?
Boiling water.
Boiling water. What else? The what? The house, as far as the air in the house. All right. Movement of the air in the house. All right, and the final method of heat transfer is radiation. So again, just write the first line. Radiated heat energy travels as an electromagnetic wave. Okay, so y'all see how the units connect? Did we not just talk about electromagnetic waves? So conduction is where we're looking at transfer of heat in solids. Convection, you're looking at the transfer of heat between materials as fluids. Can be a gas, can be a liquid. And then here we have radiation, which is looking at the transfer of heat through electromagnetic waves. So what were some of the electromagnetic waves that we talked about? Microwave, what else? Gamma rays, okay. Infrared rays, I'm sorry? X-ray, those are all electromagnetic waves, okay? Okay, so it says sometimes these waves are in the visible part of the spectrum, like when something is red hot. Okay, you can actually see it actually puts off colors. You can see how hot it is, but you can also feel it from a distance, all right? So that would be your radiation as your skin absorbs the energy. So if you see something like this, like you can see it being really hot, but you can also feel the heat from a distance. The heat lamp puts off heat that you can feel. That's radiation that you're feeling. Sun, okay, as far as the energy that we get from the sun, the heat that we feel from the sun, the heat's traveling to here, to Earth, by electromagnetic waves, the ability to travel in that empty space. So those would be some examples. Again, that's the third way that heat is transferred. So down here, you can't really see the question. Well, actually, you can see it. It says, do you think that radiated heat needs a medium to travel through like heat transferred by convection does? So convection was looking at fluids. You're talking about particles. Do you think that radiated heat needs a medium to travel through? So what we know about electromagnetic waves, does it need a medium to travel? No. Okay, it can travel through empty space. All right, and that does it for this set of notes.